Hi everyone, my name is Lydia and this is what I wish they taught me about econometrics and introduction. In the previous video, we talked about the z-table being organized to read probabilities from values, and the t-table organized to read values from probabilities. They were just different ways of slicing the same area under the curve. One repeating element or concept that came up whenever we talked about these areas was critical values or extreme values. Now, z-tables, t-tables, critical values, they are all tools for answering one question, which is, if the null hypothesis were true, how surprising is it to see what we observed? That's it, okay? A z or a t-statistic measures distance from 0 in standard deviation units. And obviously, bigger absolute values means you've got more extreme outcomes. But distance alone is not a probability, okay? So, z or t-stat, distance from 0 in standard deviation units, but keep in mind, distance is not the same as probability. So just don't use them interchangeably. What that means is that tables are basically translating distances into areas. So the z-tables are supposed to do it directly unless you have a table with a special legend that indicates otherwise, and t-tables do it via cutoffs. Both are basically converting the distance into tail areas. And that tail area is basically the probability under the null, and this is also what we will call the p-value. So in here, this is our t-distribution, and we're saying the distance from 0, this is our distance in 0 in standard units. Then the tail area in here under the null hypothesis, keep in mind, is your p-value. So if you think about it, this is where all of these extremes were that we talked about in the interpretation of the t-table. There, okay. So the p-value, as you can see, always starts with the null hypothesis. The null hypothesis, keep in mind, so finally we'll have a look at what this null hypothesis that we're adding everywhere is a story about the world. Okay. And it can say, suppose there is no effect, suppose the coefficient is 0, the p-value always asks a question conditional on the null being true. Okay, so whenever we say here under the null, what we're saying is the null is true. Okay, and this is an assumption we're making, or a condition that we're putting. Okay, now imagine the world under the null. If the null hypothesis were true, that means that your test statistic would follow a known distribution, be that a normal or a t-distribution. That distribution is going to tell you what values are typical and what values are rare. This distribution basically represents a random variation. So it's not really the truth about this world, but it's the randomness of this world. So where do the estimates sit? So you can compute your estimate through this test statistic. So you locate the value on the distribution. So imagine on this particular distribution in here that we have a value that is right here. Okay, so this value looks to be quite far away from 0. Okay, the further away from 0 it is, so it means if I were to extend this a little bit more and have like even more of the tail in here, the further away I'm going in this direction, the more unusual it would be that the null hypothesis were true. Okay, because it means I'm saying something very extreme. It's likely, it still can happen, but very unlikely at the same time. So the probability of that happening is getting smaller and smaller the more I go towards this tail, basically. Okay, so the further it is from 0, the more unusual it would be if the null were true. Okay? Now the p-value is basically the probability of observing. So based on this, so probability of observing a result this extreme based on a certain number that you have, or more extreme, again, assuming the null hypothesis is true. So visually, once again, it's the area in the tail beyond something that you observe. So let's say that this is your distribution. I'm just going to exaggerate the tail here for the sake of it, but keep in mind this is 0, and I would have done it symmetrically on this side as well. So if, let's say, this is my t-statistic that I expect to observe, and then I end up looking at a value that it's here or that it's here, it means I'm looking at something that is more extreme than that, and it's something that is even further away from 0. So I am seeing in the area in the tails beyond these observed statistics, basically. And this area in here, that's my p-value once again. Keep in mind, the p-value is not the probability that the null hypothesis is true, okay? So don't use them interchangeably. It is not the probability the result happened by chance. Okay? And it is not the size of an effect either. Okay? The null is assumed true, not tested probabilistically. Okay? So the p-value measures surprise, in a sense. So something that is quite extreme and that we weren't expecting to see. Let's interpret a little bit large versus small p-values. A large p-value will mean that your result is typical under the null, because if your p-value is large, it's very likely you're looking at a big area like this. However, if your p-value is very small in here, it means, well, your result will be very, very, very rare under the null. So the null is struggling to explain this result that it's finding. It could be that for whatever combination of samples, observations that you got in there, you ended up seeing this result, but it's really finding it difficult to explain it through the rest of the data, okay? So to iterate, a p-value is the probability of saying something this extreme or even more extreme, assuming the null hypothesis is true. This is a very key concept, especially because when you do null hypotheses, you most of the times will use what I will be calling the p-value approach rather than the t-tests or any other kind of test, because the p-value just makes it a lot more easier to get to the result. So now that you know the intuition behind it and also the visual of it, stay tuned and we'll see each other for more exercises on hypothesis testing in future videos.